First of all, thanks to the organizers for this wonderful workshop and giving me this opportunity. And also, I'd like to acknowledge Prateek, with whom I've done several projects, and part of those projects I've included in this overview talk. And I'll also like to thank Adam, with whom we had several discussions, and he has suggested several things that helped in formulating several problems in this work. Okay, so in this talk I will discuss this very simple and generic learning theory framework called empirical risk minimization. And then I'll talk about how differential privacy fits in this framework, and how this framework gives a very sort of natural and simple to understand context for differential privacy. It will give us very crisp and precise goals as to what we want from our differentially private ERM algorithm. And then I'll talk about two very popular algorithms in this area called output perturbation and objective perturbation. Both of these algorithms were initially proposed by this very nice work by Komalika Chaudhary, Claire Monteleone, and Anand Sarvate. And then I'll very briefly discuss stochastic gradient descent methods, which can be sort of thought of as more practical algorithms for solving these differential privacy or privacy preserving empirical risk minimization type of problems. And I'll briefly talk about some other empirical risk minimization settings called kernel function based empirical risk minimization. And then I'll conclude with summary and some open problems that I think are interesting. So let me start with some very basic learning problems. So let's say I have a classification task where I have a bunch of images, let's say of chimpanzee and human beings, and I want to learn a classifier so that given a image, I want to figure out what is the label of this image. So here I have data points, and the prediction that I want is whether a image belongs to class 1 or class 2. Now I need not have this discrete prediction. I can have more continuous prediction. So here let's say I have a data point that is represented by one variable, and on y-axis I have the predicted variable, and now I want and this y variable that I'm trying to predict can be continuous, and I just want to figure out given x, how do I come up with a reasonable value for y. Okay, and things can get much more complicated, such as let's say ranking, where let's say you go to any search engine, type some query, and then the search engine will show a ranked list of documents. So now how the search engine comes with this list, or how with this ranking? So again, this is a simple learning problem. And in all these problems, what happens is that I want to select a hypothesis from a fixed class W, and I'm given some instances or some training data. Let's say x1, y1, x2, y2, and so on till xn, yn. And here xi represents the data point, and yi represents the prediction that I want to make, or my target variable that I want to predict. And now the goal in learning is to come up with a function that given x1 will predict y1, or given xi predict yi. Okay. So here, if you do not make any assumptions on how training data is sampled or how training data is coming, then it's hard to study the problem. So a very simple and generic framework here is to consider a uniform sampling based approach, where what I'll assume is that each data point xi, yi is sampled from a fixed distribution D. Okay, and now I also have a loss function that for given hypothesis will tell me how well I did for an instance x. So whether my prediction on this data point x according to this variable w, or this hypothesis parameter w, matches y or not. Okay, and now my goal will be in expectation minimize the risk that is incurred by my hypothesis selection, by my selected hypothesis. Okay, so this quantity I will call as the risk, and now if I knew the distribution, maybe I can directly try to optimize this quantity, but problem is that I do not know the distribution. I only have the training data. So I'll use my training samples as a proxy for the distribution. That is, rather than directly trying to minimize the risk, what I'll do is I'll compute my empirical risk and try to minimize that. So I have these training data points xi, yi's, each coming IID from the distribution. I'll try to minimize this average loss of my W over these set of training instances. Okay. So here in this talk, I will mostly focus on cases where my loss function is a convex loss function, which is not necessarily the best thing in practice. Typically, so for example, let's say classification, I want my misclassification rate to be very small. And misclassification rate is non-convex. But then in learning theory, people have come up with these surrogate loss functions or convex relaxations of these non-convex loss functions. And what they say is that, okay, I'll try to minimize or focus on this convex surrogate. And then because of this convex relaxation, I will have some extra error that they will try to separately measure or separately estimate. Yeah.
Loss function convex also in the yi or just in the xi and w?
In w, xi, yi.
Also y.
Yeah. So xi, yi can be thought of as just one instance.
So usually for linear threshold, you multiply yi by w dot xi.
Yeah, so that's something that I'll just consider that entire space and I'll just focus on w for now. Okay. So now, so what I can try to do is I can optimize the empirical risk now. However, because even though if my loss function is convex, still I can have multiple solutions, and some solutions might be more desirable than the others. So I can try to regularize, or I can try to guide my search to a particular type of solution that I think will be very good and might have a small risk in future or on my test samples. So basically, the standard idea is to add some sort of regularization. So what I'll do is I'll try to, in this empirical risk, I'll add a regularization function. So here RW will be called, I'll call it regularization function, and lambda is the regularization parameter. Okay. So RW is a fixed function that I'm assuming is, let's say, one strongly convex. And what is strong convexity guarantees is that now I have a unique solution to this problem. I cannot have multiple solutions. And RW is in some sense putting a prior on what type of solutions I'm looking for. Okay. And lambda is my regularization parameter that I'll set appropriately to get best results, either using some sort of validation set or using my theoretical bounds. Okay. So let me explain what do I mean by strongly convex. So well, what it sort of says is that if I have a, so if this is my function Rw, then I draw a gradient at W, then my function value at W prime is at least this W prime minus W square larger than what I would have got here at the gradient. And that is considering it to be linear function. So it says that my function is growing much faster as I go far away from my optima, and that helps guide the search process very well, and in fact also ensures uniqueness of the optima. Okay. So throughout this talk, I will assume that we are trying to solve this regularized empirical risk minimization problem. And let me now give some concrete examples for this problem, like for some instances of regularized ERMs that are very popular in practice. So one of the most popular example is support vector machines, where the loss function is what we call hinge loss. So it can be thought of as a convex relaxation of the 0-1 loss that I earlier talked about. So it looks something like this rather than this. Okay. And the regularization function here is just a 2-norm of the parameter vector W. Okay. Another very popular learning problem is L2 regularized logistic regression. Logistic regression can also be thought of as a relaxation of the 0-1 hinge loss, 0-1 misclassification loss. However, this is a slightly more smooth loss function. It is differentiable. So in certain type of analysis, that helps. And it also helps in guiding the optimization procedure. Okay. And then final example is the standard ridge regression, where the loss function is L2 least squares loss function, and again the regularization function is the L2 regularization function. Okay. All right. So as I said that in reality we want to solve this true risk or population risk. But what we are doing is either empirical risk or regularized risk minimization. Okay. So the question is how much are we going to lose because of this? And because of this finite number of samples, how much excess error I am going to incur? So for these problems, there exist several results, some very generic results that bounce the excess error incurred because of solving a proxy problem to the original problem. Okay. So one of the most popular result here comes from this work by Shai Shalishwaz and colleagues. So there they say that, okay, let's say I fix a distribution D, and I'm assuming that if data point x and y are sampled from this distribution, then almost surely norm of x is bounded by some quantity bx. And similarly, let's say I will focus myself on looking at this hypothesis from this fixed hypothesis class w, and I'm assuming that norm of every vector w in this hypothesis class is bounded by bw. Okay. And I'll also assume that the loss function is convex and L Lipschitz. That is, if I vary W1 slightly, then the loss function does not change too much. Okay. So under these assumptions, and over the probability of over the randomness of sampling these training data points, what we can say is that for every W in my hypothesis class, the population risk is very close to the empirical risk, and the closeness or the excess risk that we are getting is this much. So this goes down as something like 1 by root n, and it has this quantity of Lipschitz constant and the radius of the ball in which we are working. So this is very similar to the Chernoff bound. Only issue is that now we are taking a soup over W. So the W can itself depend on all the variables. So in some sense, what this bound is doing is it is taking a covering number argument or doing a covering number argument in a slightly intelligent fashion, so that explicit dimensionality is not showing up. Dimensionality is in some sense implicitly showing up in terms of the norms of X and W. Yeah.
So the star is any arbitrary norm?
Yeah, sorry. So if I'm measuring x in some norm, then x star is the dual norm of it. So it's the dual norm. Okay.
And what's the quantification on C?
I'm sorry?
What is the quantification on C?
C is any constant. I didn't put to
Fixed
use.
before what?
So C is a global constant.
It's like 7. It's like 7.
7.
42.
No, it's small. It's not that big. 42.
Okay.
It's really like 5.
So so now this says that my empirical risk and sample risk differs by something like 1 by root n only. And this is also in learning theory, it's also called uniform convergence bound because it holds for every W in my hypothesis class. So now let's say I'm doing empirical risk minimization. I obtain W tilde by solving this proxy problem, whereas W star is the optimal thing that I can do. Yeah.
Prateek, in the last slide, did you? So you're bounding the norm of X, but are you assuming anything about the form of the loss function or?
No, here you
why,
don't. Here you don't need to assume anything. For this.
Just that it's Lipschitz for every pair
Just
X,
as
Y.
Lipschitz, yeah. So, okay. So now.
Sorry, Prateek, quick question. I want to follow up on
Yeah.
that. It's not Lipschitz in X and Y, only in W.
Only in W, yes.
It can vary wildly with X and Y.
Yeah. So why does the norm of X have anything to do with it here?
For every X and Y, Lipschitz over W.
Over W.
We're going to change the X slightly.
Could change a lot.
When I do IID samples, usually
Yeah. Usually we assume that the Lipschitz continuity thing is L times the norm of X times the dual norm of W1 minus W2.
Oh, okay, yeah, yeah, I think so.
That
So
would
yeah,
make
here
sense. Yeah, that would
it
make more
will
sense.
show up
L
in
times
the
VW or something.
yeah.
It's just this.
Okay. Yeah, so it should be L times Bx and something. So now, because we are so we are trying to find out the best, or we are trying to compare ourselves with respect to the best W star for sample risk. Whereas, let's say we find out a W tilde by doing this empirical risk minimization. So now what we can say is that because my empirical risk and true risk is so close, and furthermore because I'm doing this optimization over empirical risk, that's why Rn W tilde will always be less than Rn W star. And that's why what it will say is that if I do empirical risk, then the excess risk that I'm getting is of this type. Okay. So now let's say when I'm handling this regularized empirical risk minimization, then I have some more structure because I know that my objective function is strongly convex. So in that case, can I improve my bounds? And the answer is yes, but in some restricted sense. So again, the assumptions are similar. Again, I think you will have L and the norm of X here. And we are assuming that L is one strongly convex. So in that case, what you can say is that if W hat is the minimizer of this regularized ERM, then objective function value of W hat is less than the best objective function value plus something that goes down as 1 by n. Okay. So this rate is much better. That is, I'm getting this rate at 1 by n rather than 1 by root n. But I can make this statement only for W hat, for my minimizer only. I cannot make it for any arbitrary W. So I don't have uniform convergence in that sense. Okay. So, but this still seems very weird that I know that even if for a fixed W, my Chernow bound cannot give anything better than 1 by root n. Then how am I getting this extra thing? So, well, answer is that because now when I'm doing this risk minimization, I also have this extra factor of the regularization parameter. So here, when I'm trying to bound RW hat, this will be bounded by RW star plus this extra regularization parameter, and then I have to set lambda properly to balance it out. And when I try to set lambda appropriately, it will turn out to be something of the order 1 by root n, and that's why again the rate that I'll observe will be 1 by root n only. But now nice thing is that in my rate, what I will have is R of W. So it won't be in earlier case the bound was in terms of the radius of the hypothesis class. Now it won't be that. It will be what is the minimum possible of RW for a good minimizer. So let's say if I had 100 minimizers of my empirical risk, then out of those 100 minimizers, whatever minimizer had the minimum value for RW, I can use that. Okay. All right. So now having set up, explained all the empirical risk minimization framework, let me just set up the notation so that now we can move on to differential privacy versions of this empirical risk minimization problems. So I'll assume that the data is in my data set. I have n points. Each of the point is in R to power d. I'll assume that norm of x is less than or equal to 1, and each of the data point is sampled from this distribution d. And empirical risk, sample risk bounds are anyways clear, and uniform convergence bound gives us this rate of 1 by root n, and then W star throughout the talk I will use for the best minimizer or best solution for my real problem, that is true risk minimization problem, and W hat will be the optimal solution to this regularized ERM problem. Okay, and we have this bound for W for the excess risk incurred by W hat. Okay. All right. So moving on. So now we want to solve this empirical risk minimization problem, but while preserving privacy of each of my data points. So here in this empirical risk minimization problem, what's going on is I have these training sets. Will have a learning algorithm that will output this W hat. And what I want is that this W hat is differentially private with respect to the given data set. And furthermore, my algorithm or the W hat has the risk of W hat will be small. Okay. Excess risk is small. Okay. So now there is a question that why is it even possible? Like, why do we think, or what is the intuition why we think that we will be able to achieve this task? So, well, the idea is that we added the regularization just to ensure that we do not overfit to the data. That is, our hypothesis is stable to small changes in the data. And that's precisely the type of condition that you want your differential private algorithm to have. So, I'll try to precisely state what do I mean by this stability and how, and I also actually give the proof. The proof is like just 3 lines. So I'll give this, and I'll call this lemma a convex stability lemma that Adam called in his talk yesterday.
To be clear, I don't deserve any credit for.
No. So I'm not saying that. It's just that the nomenclature is the first time I heard. So I thought it's a cool name. And it comes again and again, so maybe we should have a name for it. So let's say I obtain W hat by solving this problem over data set D. And let's say I have another data set D prime that varies or that is different from D in only one data point. And for simplicity, we'll assume that only nth point is different. Okay. And if we use this data set D prime, then my solution will be W hat. W prime. Okay. And now by stability, what we mean is we want to bound how much W hat and W prime can differ. Okay, and the lemma is that it differs as something like 1 by lambda n or L by lambda n. So the proof is extremely simple because we know that for this objective function J, W hat is the optimal. So for all W's, this quantity is greater than or equal to 0. And by strong convexity, I know that my objective function at W hat is less than objective function at W prime plus the gradient plus this strong convexity term. Now gradient is always greater than or equal to 0, so I can ignore it and I will obtain this equation. And similarly, I'll use same equation but for my second optimization problem, that is for this optimization problem, because W prime is optimal for this. So I will obtain a analogous equation here. Okay, and now I add these equations up. The regularization parameter or these regularization functions cancel out, and what I will observe is something like Rn W hat minus Rn prime W hat and Rn W prime minus Rn prime W prime, and I want to bound them. But note that because my data sets D and D prime differ in only one entry, so Rn W minus Rn W prime is given by exactly this for all W's. So we apply this twice, and that's why this n times lambda W prime minus W hat square is given by some of these loss functions, and then we use the property that L is Lipschitz, and that will give us this bound. And we cancel out W prime minus W hat from both the sides, and we show that the W prime and W hat are differ by at most 1 by lambda n. So as my data points are increasing, or if my regularization parameter increases, then there is the two things are more stable. And now because we know that if my output that I'm giving is stable or has this type of sensitivity, then I can add noise of that level and make the algorithm differentially private. So that's precisely what this algorithm called output perturbation does, which was first proposed in this work by CMS 11 and RBHT 11. So the algorithm is extremely simple. Let's say this is the objective function that I'm trying to minimize, and for simplicity, let's say I don't have any constraints and all, so W hat will be the optimizer. So W private is W hat plus some noise. Okay, and in this work of CMS 11, they propose to use the gamma noise or Laplacian noise. Okay. So what they show is that this output perturbation algorithm, which is extremely simple, is epsilon differentially private, and furthermore, the utility guarantee is of this type. Okay. So here the utility is in some sense optimal in terms of n and epsilon, But there are two interesting terms appearing in the numerator. One is a D. So if you remember in the excess risk bounds that we give for non-private empirical risk minimization, we didn't have any factor of D. It was characterized by how the norm over my set looked like.
Sorry, you say that's optimal in terms of epsilon?
Yeah, I mean 1/7 is.
That seems strange to me because we can get those types of results in the local model. So the global model, we should have much better dependence on epsilon, right?
Epsilon might go inside the square root also. I'm not sure about that.
In the local model, it would be epsilon
root
squared times
N
n inside the square root. So it feels like in the global model, our dependence on epsilon should be much, much better. I mean, I think that's what we usually
But I don't remember of any result that has something like 1/root n epsilon.
But we don't know if that's optimal.
Okay, so I'll take that
no,
back.
I'm asking.
Yeah,
do we know
I
if
don't.
that's
So
optimal?
it seemed like
I don't know that that's optimal.
pretty good dependence, but I'm not sure about.
It just
Well, how about in one dimension?
I think you could probably.
in one dimension, I think it should be
Very
1
good.
on root n plus 1 on epsilon squared n. I think. Because the amount of noise I add in one dimension, if things are sort of 1 on n sensitive, is
1/epsilon square is much worse.
but I have an n on the bottom of the.
Oh,
That's okay. It's fine.
yeah.
Okay,
so
it seems like
the
we don't
best
have-
I have
it
seen
seems
so
like
far
there's
is
not a-
1/epsilon. So
No one has an immediate answer, so
yeah.
that's fine. That sounds like.
I
Okay.
think it's epsilon goes inside the
But-
square root. And I think that's probably.
Okay, so there are two quantities here. One is that we have this term W star or 2 norm of W star, and then there is a dependence on dimensionality. So this dependence on dimensionality is something undesirable, but this dependence on W star is very interesting. So this sort of says that if, let's say, my optimal solution has very small norm, then even my differential private algorithm will have fairly good excess risk, right? And this W star in some sense characterizes how hard the problem is. So for example, in the case of support vector machine problem, or in case of this binary classification problem, my margin is given by 1 by norm of W star. Okay, so if the margin is larger, that is, if the problem is easier, then the norm of W star is smaller. Okay, so that is correctly characterized by this bound, although the exponent 4/3 might not be optimal. Okay, so later on in this work by Kiefer, Smith, and Thakurta, they proposed to use Gaussian noise instead of the gamma noise, and that immediately buys them a root D factor here. But they lose in terms of privacy guarantees. That is, now you will have only epsilon delta differential privacy. So now the question is that can we do better? Can we get rid of this D entirely? So in recent work with Abradeep, we showed that if we assume that we have generalized linear model, that is the way W and so basically we have a linear model and L is just a convex function over this linear model. And if the regularizer is the L2 norm regularizer, then using the same Gaussian noise, we'll have epsilon delta differential privacy, but the dependence on W star is now optimal and there is no dependence on D. Okay. And here I would like to stress that the generalized linear model is very important, because in general, if you are trying to solve the problem, getting rid of D might not be possible. For example, if you are computing mean of n vectors, that itself will throw in a dependence on D. But because we are just restricted ourselves to linear model, generalized linear model, which is very common in learning problems, like in fact almost all the learning problems of interest like classification, regression, etc. has generalized linear model. So that is well motivated. Yeah.
Is this specific to this bound is specific to expected risk? Is that right?
Yeah, this is specific to expected.
So if you wanted like high probability bounds, that dimension might crop up again. Is that correct?
No, but you cannot do any better than expected risk, right? So this is true risk, as in on any sample of from a distribution.
Oh, right.
What will be my loss?
I think the question is,
No, you can
what's the probability that W private is actually bigger than the terms on the right-hand side?
So the probability will be, well, it will be a constant probability only. We cannot guarantee better than constant. But we can get something that is decreasing in D by adding an extra log factor. So I'll show you how the probability comes in. And so the observation is extremely simple, that because we have this output perturbation algorithm, so whenever we try to measure how different the prediction of W private on X will be from W hat X, well, that is given precisely by inner product of B, which is a Gaussian noise, with X. And because B is a Gaussian noise, so inner product of B comma X, and B is independent of X. So this random variable now doesn't have any dependence on D. It's just a N0 variance random variable. And now here we bounded this by something like by L by N lambda epsilon using constant probability. But if you want something that is going down with dimensionality, you have to add an extra log D here. And now because my loss function is Lipschitz, so the difference between the loss function is bounded by how different the prediction or projection onto vector X is. Okay, and this will then using uniform convergence bounds will immediately imply that the risk at W private is less than or equal to risk at W hat plus a term of this type. Okay. And then using bound on RW hat and then trading off our lambda properly, we obtain this utility guarantee or this excess risk guarantee. Okay. So the proof is okay. All right. So let me move on to now another algorithm, which is objective perturbation. So the issue with output perturbation is that it seems like you have completely solved the problem and then you are adding some noise, and it might so happen that maybe the data was also very well conditioned, might have good condition number, and in that case we are unnecessarily adding too much of noise. So if we perturb the output objective function itself, then maybe if the data is well conditioned, then that will automatically give us better results. So that was sort of the intuition behind doing this objective perturbation algorithm. So what we do is, this is our original objective function, and we'll add a small noise to it. And in terms of geometry, what it says is that if this function is the true objective function that I want to minimize, and let's say W hat is the true minimizer, then my gradient will be equal to minus B for this objective function, and W private will be given by this point, wherever the gradient intersects this curve. Okay. So now for this algorithm, this work of CMS 11 showed that the algorithm has epsilon differential privacy because they add this gamma noise, and furthermore the excess risk that they obtain is of the order of the type W star D by root n. Okay, and then this work by KST12 showed that if you add Gaussian noise, then you can indeed do better. You have something like root D by root n with this W star. Okay, and this work also improved analysis of this work by Komodika and co-authors in a very significant manner. So that work needed to assume that the objective function is differentiable, especially the regularization needs to be differentiable. Whereas this work showed that you do not need that property, and that was very critical because they were interested in sparse linear regression where the regularization function need not be differentiable. Okay. Also, I'd like to mention that because we are adding Gaussian noise, so you will obtain only epsilon delta differential privacy. Okay.
So maybe you said it on the previous slide, but this method also requires.
So this is not actual method. Like you need to add some like regularization also, small amount of.
Right, but doesn't it also requires some some extra smoothness on this, the little loss on little l, no? Doesn't it?
Yeah, you'll need that L is, the Hessian of L is bounded.
Right.
Yeah, so I'm
You're
ignoring
slipping
that
into
for
the-
now.
okay.
Okay, so, all right, so this is very good, but still we are getting this extra root d factor, and the question is, can we get rid of that? So answer is yes, but under, definitely we need to assume generalized linear model, but we also need to make two very sort of restrictive assumptions, or they are reasonable assumptions, but we would like to relax them. So one is that the regularization function is L2 normal, or sorry, L2 square, and the problem is unconstrained. So under these assumptions, what we can show is that you can obtain a excess risk bound, which is not dependent on D, and which is dependent on W star as the optimal risk bound. And that is non-private version of it. So the only extra factor that we are getting is root log 1 by delta divided by epsilon. Okay.
Can you remind me how this compared to the output perturbation bound?
So this matches exactly the output perturbation bound. But in practice, this method tends to be much better than output perturbation, because it is able to utilize the intrinsic strong convexity in the data points itself. Okay, so let me give a very brief proof sketch of for this analysis. So remember that we have this output perturbation, objective perturbation, and then we have this L2 loss function, and we have unconstrained problem, and that's why what we can say is we can sort of rewrite this optimization problem by just clubbing these two terms together, and then I'll add b by lambda and subtract b by lambda. Okay, so now we will treat this w plus b by lambda as one variable v, and we can define this new loss function, which is also a empirical regularized empirical risk minimization problem, slightly perturbed than our original one. And what we have is that if v tilde is the optimizer of this regularized empirical risk minimization problem, then w private and v tilde are related by this quantity.
I'm just looking for lambda prime.
So this is lambda. I think it should be comma, and
Oh,
it's okay. So now that we have this characterization of w private and v tilde so closely, what we can do is we can, for this regularized ERM, we can apply the excess risk bound, which I presented a few minutes back. And recall that this risk bound also dependent on the norm of the vector, so that comes as inner product of dx by lambda square. I'm assuming that norm of x is 1. Okay. And now we know that h of v tilde is equal to the sample risk at w private plus some regularization, which is positive, so we can ignore that. And on the right hand side, we have something like risk at w star minus b by lambda plus norm of w star. Okay, and because my loss function is Lipschitz and I have generalized linear model, so I can relate empirical risk at w star minus b by lambda and empirical risk at w star, and the difference will be something of the order inner product of bx by lambda times something. Okay. And again, we'll use the same fact that because x is independent of b and b is a Gaussian vector, so this quantity is of at most of, let's say, order log d with probability that is decreasing polynomial in d. Okay, and that will complete the proof. All right, so let me now briefly present some experimental evaluation for these two type of algorithms. So one approach is do output or objective perturbation, but with a gamma noise. So these are given by this black curve and blue curve, and do this output and objective perturbation, but with Gaussian noise. And here we can see that if, let's say, we artificially boost the dimensionality of these algorithms, or sorry, of the data set. So our original data set is in only 8 dimensions, but we just padded it with zeros. And just because of this padding, the original output and objective perturbation algorithms performance decreases very sharply. whereas this Gaussian noise-based method still remains at the same level of accuracy. Another very important point to note is that there is a big difference between the performance of objective perturbation and output perturbation. So the baseline accuracy is around 91%, and objective perturbation is able to achieve almost that accuracy, but output perturbation is like 15% lesser than that. Okay, so so far what we did was we considered this empirical risk minimization problem, considered these two very generic algorithms, and we showed that if we have L2 regularizations on this problem in our problem, and the problem is unconstrained, then we can have a excess risk bound that is independent of dimensionality. But then we wanted to consider some other problems where, let's say my regularization parameter is something different. So another very popular regularization parameter is the entropy. So now what I will try to do is I will try to do optimization over the simplex or the probability simplex, and the regularization parameter is the entropy of this probability distribution, or negative entropy of the distribution. So we want to understand what will be the excess risk of this regularized DRM. And there exist several motivations for this entropy regularized empirical risk minimization, for example, in several machine learning problems like facial expression. And also by analyzing this problem, we were able to improve regret guarantees for the online experts problem in differential privacy context. Go ahead.
Is there some relation between the choice of the regularizer and the norm that you choose to, like,
yes,
the norm constraint for W? Like, is there like a general principle?
Yeah, there is a simple principle, that is your regularization should be strongly convex in the norm. Which was the requirement? Yeah. So whatever norm you select, so let's say entropy is strongly convex with respect to the L1 norm. So so over your hypothesis class, now you will try to put your L1 norm, and now on the ball from which your instances are drawn, you will put the dual norm, that is the infinity norm. And that's a very general principle, and like that principle has been explored very well in learning theory and optimization literature. Okay. So now for this problem, we do not use objective perturbation or output perturbation. We came up with a sort of different type of algorithm based on sampling, and that seemed to give us very good dependence on dimensionality. So the algorithm is very simple, that because I am learning this W hat, which is a probability distribution, so it will look something like this over D dimensions. Now what we'll do is we'll sample this distribution m times, okay, with this probability distribution. So we'll have these m samples, and now the estimated probability vector that we want to give and which we want to claim is differentially private is just given by summation of these samples, but or canonical vectors of these samples. So here EI means ith canonical vector, that is it's 1 in the ith coordinate and 0 everywhere else. So one immediate thing to note is that in expectation our private output is still same as W hat. Okay. So now let's see if we can show some privacy guarantees for this algorithm. So one thing to note is that if I take infinite samples of from this distribution, that is if n tends to infinity, then I cannot hope for any differential privacy because I'm giving you back exact W hat. So I have to bound the number of samples that I can take. So the way we bound the number of samples is given by this. And we also use the fact that because the algorithm is entropy regularized, or the ERM is entropy regularized, so it will tend to push towards uniform distribution. And furthermore, so that brings in some sort of regularity over the probability space. And furthermore, we can sort of say that the probability vector that we have is of this particular type. So this looks suspiciously similar to a exponential mechanism. We can use analysis similar to exponential mechanism, apply strong composition theorem, and get epsilon delta differential privacy. And one thing to note is that we also have to assume that the loss function that we are using is smooth. That is, the gradient of loss function is also Lipschitz, continuous. Okay. So this is the privacy guarantee. And now for utility guarantee, we just sort of use Chernow bound because we are taking these m samples and we are averaging them, and we know that in expectation it is exactly same as W hat. So using Chernow type of bound of argument, we get this type of loss. So the key thing in this excess error is that the dependence on dimensionality is just logarithmic, which is optimal even for non-private algorithm. Even a non-private algorithm will have log dependence on D. However, our dependence on N and epsilon is very poor here. So in particular, our dependence on N is something like 1/3, which is certainly suboptimal, and it is certainly an open problem to make this better. But one interesting thing about this is that the way we estimate W private is by taking this, by adding these N canonical basis vectors. And that's why we can bound the number of non-zero roughly by n to power 2/3. So if my dimensionality is very large, then the private output that we obtain is very sparse, even though the original vector W hat was dense. So this is very interesting because now when I'm trying to, at the prediction time, the prediction cost is very small because I have to just take something like order n to power 2/3 multiplications and add them, rather than doing order D computation. So this is interesting that differential privacy, so rather than doing exact computation and then perturbing it, if we are saying that okay, we'll already perturb our computation, then that might help in several aspects for differential privacy. For example, here it's helping in the prediction cost. Yeah.
So what should be the right dependence on N? So if
It should be
non-private dependence?
root N. Well, so let me summarize the results that we have seen so far for various regularized empirical risk minimization algorithms that we have seen. So if we have output perturbation with gamma noise, then we have correct dependence on N, but there is a dependence on D, and dependence on W star is also not correct. But if we have output perturbation with Gaussian noise and in generalized linear model, then we have the correct dependence on both W star and N and D. And similarly, if we have objective perturbation with gamma noise, then we have a dependence on D. But if we have objective perturbation with Gaussian noise, generalized linear model, and L2 regularization, then the dependence on D goes away, and the dependence on W star is also optimal. And finally, if we are solving an ERM that is regularized by entropy and is constrained to lie on probability simplex, then our dependence on D is optimal, but our dependence on N is still suboptimal. So this is the summary of results that we have seen so far. So far, like in both output perturbation and objective perturbation, and even in the sampling based algorithm, we assume that we solved an optimization problem exactly, and then we perturb it or solve a non-perturb problem. But one main issue with that approach is that in practice, we do not have optimal solution from an oracle. We have to run some sort of optimization algorithm, and there is a budget on how long we can run that algorithm. So, and these algorithms or these analysis directly does not guarantee that if, let's say, I stopped after, let's say, 50 iterations, what will be my privacy guarantees. So we need to study some more, need to study differential privacy of the iterative algorithms that are popular in practice to say that, okay, these iterative algorithms are also reasonable from differential privacy point of view. So there has been a lot of work in this direction. So in the standard model, that is where you are outputting just one W hat and all the data is with one server or one learner. And there, in this work with Prateek and Pravesh, we showed that stochastic optimization methods have differential privacy and had reasonable utility guarantee. And then in the local model where the person who has the data does not even trust the learner, there John and Michael Jordan and Martin Wainwright has some results for stochastic gradient methods. And couple of days back, Anand presented some results for mini batch version of the stochastic gradient descent methods. Okay, so let me very briefly describe the stochastic gradient descent method and how we can just add noise to obtain differential privacy guarantees here. So let's say this is our regularized empirical risk minimization problem. Now typically we will try to do gradient descent here, and how a problem is that the gradient descent is very expensive because I have to compute this gradient over n points, and all of them are in d dimensions, so it might be of order nd. So the learning community sort of seems like have converged to this solution that yes, let's use a stochastic version of this gradient. So rather than computing the entire gradient, I'll select one data point from my data set and compute its gradient and update the solution. And in expectation, I'm doing the correct thing, and it so turns out that with high probability also this will give a good result. Okay, and the way to analyze such algorithms is, yeah.
So after how many, for what values of t? So what I've seen in the literature is sort of a comparison of what you get with the batch version with endpoints versus stochastic version with n log endpoints.
So what this does is that so you have to select eta to be, let's say, something of the order 1 by root t or 1 by t, depending on if your loss function is strongly convex or not. And what it says is that if I want a quick and dirty solution, then this algorithm is very fast. But if I want exact solution, then after some iterations, this algorithm will not, like the progress that it makes is very slow, but the true gradient descent will be much faster. However, one argument for this stochastic methods is that the data that I observe is anyways noisy. So why do I want to optimize it completely? And that's why such methods have become very popular. Okay, and later in the talk I will tell you about an algorithm which doesn't even respect this, like it does not even respect the regularization parameter, and that also, like, people have shown works reasonably well, at least for the learning and statistical setting. Okay. So in terms of differential privacy, well, in the standard model, what we can do is after t steps, when we are happy that maybe we have a reasonable solution, we'll add a noise and give the output. And the privacy proof comes through the stability of online learning, and utility proof comes from the standard online to batch conversion. I won't have time to go in that today. As for local model, yeah, you can add a small amount of noise to the gradient, and then again similar convergence results hold. And this is a pan-private model, that is at every point of time the solution that you have is differentially private. That is, even if you look in the server, you won't be able to violate privacy of any data point. Okay. So let me very briefly mention this annoying thing of parameter tuning, because in practice, when you are trying to solve this problem, you have to tune parameters, and that will require several reruns of the data. So one option is to do some sort of exponential mechanism, which was proposed in this work by Bhaskar, Lakshman, Smith, and Thakurta. And then recently, and like a couple of days back, yesterday we heard this very nice talk by Kamolika, which seems to suggest that we can use some more advanced techniques to exploit the structure in the problem to do parameter tuning in a better manner. Okay. So now I will move away from the standard empirical risk minimization problem where we were just working in generalized linear model. I'll try to talk a little bit about the kernel function based empirical risk minimization problem. So first, let me give motivation for why do we want to worry about this kernel function based ERM. So in all this work that I have talked about so far, there is in some sense an inherent assumption that the data is nearly linearly separable. That is, like there can be a few points which are non-separable, but at large the data is reasonably separable. But in practice that need not happen. So for example, here I will need a circle to separate out these two data points, and there actually I will have 100% accuracy. But in general, this data is not linearly separable. So one of the major achievements of machine learning has been to come up with techniques to handle this problem. So one approach is that because let's say in 2 dimensions my data is not separable, maybe I'll project my data in 3 dimensions and hope that it will be separable there. Okay. So for example, for this problem, if I take x1, x2 and project it to this 3-dimensional space, then the data immediately becomes separable. You can find a hyperplane with very good margin, and you will be able to solve the problem. Another interesting thing here is that the inner product of any two data points is dependent only on the inner product of x and z in low dimensional space. You don't even need to compute this mapping explicitly. You just can compute the inner product of x and z, and that will give you the required inner product. Okay. So let me now formally define the kernel function. So suppose I have a map from R to power d, which is my original space, to a much larger dimensional space R to d phi. And in fact, d phi can be infinite in several cases as well. And a kernel function is just defined as a function over x and z in R to power d that computes inner product of these two high dimensional Hilbert space vectors. Okay, and there exist several popular kernel functions. Some are very nice and nice parametric functions. For example, this Gaussian or RBF kernel or polynomial kernel. Whereas in practice, people have come up with certain kernel functions which might not be this nice. So for example, there is this pyramid match kernel which is extensively used in vision, and computing this kernel function itself is maybe 100 or 200 lines of code. So it's not easy to parameterize such kernel function. You can at most think of this kernel function as a black box. Okay. So let me now discuss how this kernel function comes in the picture of our empirical risk minimization. So let's say I am assuming a L2 regularized empirical risk minimization problem, and I'm solving over this really high dimensional data where I'm hoping that the problem is linearly separable, and that's why the optimal solution to this problem will be reasonable. So here one thing to notice that W hat is in the span of all these vectors phi x1, phi x2, so on till phi xn. And that observation is very easy because suppose let's say I had an orthonormal component, then this orthonormal component does not contribute anything to the loss because all these phi xi's are orthogonal to W W perpendicular. But it certainly adds to my loss function, this regularization function. So this will give me a suboptimal solution. So this clearly says that W prime will be 0, W perpendicular will be 0. So now this simple observation says that okay, rather than worrying about solving for entire W hat, I can just worry about solving for alphas. So I'll reparameterize my problem, and now the problem is in terms of just these alpha hats, and there is no explicit dependence on phi. Everything is in terms of these kernel functions or these inner products, and there is an assumption that the inner products can be computed efficiently, even though computing the mapping phi might not be possible at all. Like phi mapping can be in finite dimension, for example, in Gaussian kernels. Okay. So that's great, but now the question is, can we apply our differential privacy techniques that we use for the empirical risk minimization problem that we saw in the linear case? The answer unfortunately seems to be no, because we cannot explicitly compute this vector W hat. This W hat is parameterized by these alpha i's. Okay, so this our solution itself is parameterized by these alpha i's and my training set. So if I want to release my parameter vector W hat, I have to give out the training set also. So there is no question of preserving privacy at all. And note that I am not assuming any model over the kernel function. So kernel function can come from some crazy million line code, and we might not be able to extract any good property out of it. So we have no handle on, for given 2 points, how the kernel function will look like. Okay, so this sort of says that differential privacy in general might not be possible. You had a question?
Dimensional mapping that preserves the phi space.
Yeah, but that will sort of assume some goodness of the kernel, isn't it?
It's good in L2 sense. It's assumed that it's meaningful kernel. We have a large margin in the phi space. So
Yeah, but
otherwise you wouldn't use that anyway.
Well, sometimes it's hard to figure that out, right? So.
But you know, in order to assume, I mean, you need some goodness in the kernel. Otherwise, you'll overfit, right? And so the more natural way, the natural notion of goodness is that you have a large margin, right? The usual notion of goodness. for the kernel to be useful, it has to be a legal kernel. It has to be satisfying maybe an additional property like a large margin property that allows you to get good generalization bounds. Now, if you have a large margin property, you can construct row-dimensional mapping. That is linear map, and you construct row-dimensional mapping, you get that has such that the data is linearly separable in the row-dimensional space.
No, certainly you need this large margin property, and the issue is that in rest of the work we never had to assume that we have large margin property, because whatever risk that we get is compared to the best we could have done with the hypothesis space. So in that sense, that is a stronger assumption. So the question is, can we do anything better?
So you don't get to do this just assumption free in the general kernel case, because usually if you're not making assumptions on margin or something, you're making assumptions on your kernel being bounded or something like that. That's a very strong assumption.
The kernel being bounded is
strong.
Sort of trivial. Why? So let's say for Gaussian kernel, it's...
I understand that the Gaussian kernel is bounded, but the approximation rates that the Gaussian kernel gets for interesting functions, like Sobolev classes, things like this, are extraordinarily slow. Right? I mean, I understand that we do this, but there are, I mean, you know, Nina's right. If we're getting sort of certain behaviors with the usual kernels, then, I mean, there's a lot of sort of functional analytic stuff going on under the hood that we need to be careful about a little bit. But
no, that's a good point. Right.
So maybe you'll mention this, but if I recall, maybe if Kamali can see, she can, or maybe Anand can comment that in fact, a couple of the original papers that looked at objective perturbation that you cited earlier mentioned that to deal with kernel learning, you could project from the kernel space, say using this. There's this like the sampling. Sorry. Right, Rahimian ref sampling.
Yeah, but those things require an assumption of the type that the kernel is either translation invariant or it is of the form something like exponential inner product of x, y. And that's why I say that I might not have any handle on the kernel. For example, in this pyramid match kernel, the kernel is completely crazy.
Alvin and Santosh and Hari and order work, and we can do this for any kernel. So if you give me access to label data, I can construct these mappings that kind of preserve the nice structure of the phi space and the mature dimensional mappings. All we need is access to unlabeled examples.
Do you need like
but,
to have a handle on phi?
Black box access to the kernel.
Yeah. So I certainly agree, but to bound the number of dimensions, you will need the margin assumption.
Yeah, so that's under margin assumption.
But
Like
also
you need
this-
something like 1 by margin square.
Also, it seems like the projected subspace that you will come up with is actually a function of the data.
It is a function.
Right, so you'd have
So,
to.
in the pure differentially private model, that wouldn't really be private.
Well, you would have to think about whether it's private.
You might have to have like a prior, you get a prior, then you kind of could make your own fake data that was close to the real data, and then depending on how
Or
close.
public data.
Or public.
So actually, one of the models might fit in that sense. So in general, without making any assumptions on kernel or how separation goes, it seems like we'll need to change the model a little bit. So in this work with Prateek, we looked at 3 models. So one was extremely simple interactive model where, let's say I have a database from which I get the supervised training points. There is a learner, and which learns a hypothesis or a parameter vector W. And now a user comes in, he sends a test point to the learner, and learner just needs to give out the prediction. And this is a fairly useful model for several problems, let's say in online setting where, let's say, user comes in, gives out a query, and you just have to answer the query on the fly. Okay. You don't, user does not demand the parameter vector itself. He just needs a prediction. Okay. So this model is fairly easy to handle. I'll show how we can do it. Another model is what I think Evrim was referring to, which is a sort of semi-interactive model where I have a database and from which I'm getting supervised training points. I have a learner learns something which might not be differentially private, and then a user comes in, gives his own test samples. So whatever test data he has, he takes a small number of samples from that and gives it to the learner. And now learner's job is to release a vector W, which will be differentially private, and hopefully which will work as well as possible, as well as the original W star or W hat that he learned. Okay. And so for this type of problem, either you need a publicly available test set, or you need some sort of scenario where, let's say, you have two hospitals and a research lab. Both the hospitals trust this research lab. So hospitals A sends its data, training data, to research lab to find out the hyperparameter, or let's say support vector machine model. And hospital A does not have any issue if if the research lab gives out the parameter vector, as long as it preserves its privacy. So research lab will ask the other hospital to give at least a small sample from the test set, and because the research lab is trusted, so the hospital B will give him the test samples, which definitely won't be labeled. And then using those test samples, the learner can learn a W private, send it to the to hospital B, and hospital B can use it, and in expectation it will still be very good. Okay. So, and then third model is this non-interactive model, where is the usual model, but we are assuming a parametric form of the kernel. That is, we are assuming that the kernel is clearly specified in parametric form, and it is function of these data points x and z, which are in R to power d. Okay. So let's first talk about the interactive model, where we let's say receive query zt at the tth step, and the prediction will be inner product of w hat with the phi of zt, which is then clearly parameterized by the alpha i's that the learner has. So learner has learned this alpha I hat, so it has that. So it's just an inner product of alpha I hat with k. Okay. So this is a simple linear query that we need to answer for a private database, and it's an interactive query release mechanism. So we can use this Fries-Kernel IDC approach of Gupta, Roth, and Ullman, and we can privately release this. We can release the prediction that are differentially private. Okay. So the results are that if we have t queries, then the algorithm is epsilon differentially private, and the risk for each of the query is bounded by a quantity like this. And here again we have dependence on n as 1 by root n lambda, and dependence on w is given by norm of w square. Okay, so it's the L2 norm. Note that if we have dimensionality dependence, then that will completely kill the problem, because dimensionality of the high dimensional space is infinite. So that won't be meaningful at all. So the algorithm is this algorithm by Gupta, Roth, and Ullman, which is based on this work by Moritz Hart and Guy Roth. So the algorithm is sort of so you want your prediction w hat phi zt to be, so they are maintaining a database wt at each step, and the guarantee is that the database that they are maintaining is differentially private. Okay, and now if for a given query, if my prediction with some small amount of noise far away from the correct prediction, then I will make an update. And what you can show is that the number of updates typically will be very small, because each update will decrease the potential function.
You're going to the database from the site using the queries.
So what's the form of the thing that you output? W hat is a linear combination of the kernel functions evaluated as ZT.
Yeah. So what we'll here we won't output w hat. All we will output is something like alpha hat inner product with k plus some small amount of noise. So if my prediction is correct, then actually I won't add even any noise. I will have a differential private version of these alpha hats. Let's call that alpha t, and I'll just output that. But if there is too much of discrepancy, then we will output this quantity plus a small amount of noise.
So essentially your support vectors will be amongst the test points.
Yeah, support vectors will be there among
From
the
the
test
test
points. Yeah.
So sorry. Do you ever release?
No, here
So this is
here
basically-
here
this
we
is
are
basically-
no
Kunal's
here sorry
question
support
was
vector
basically
is.
mine.
I'm sorry.
I think Kunal's question is basically mine. So you release the kernel function, the entire kernel function evaluated on these z query points.
So given a query point,
I might not be understanding.
So you create a new kernel function which looks like the original kernel function on your test set distribution, but is actually is a linear combination of your ZTs.
Effectively, you can just release the ZTs.
No,
Yeah,
these are the
ZT
test points.
ZTs
these
come from
are
the
the
user.
queries.
User is submitting Zs.
That's fine.
What you're releasing are the predictions, basically.
Are you releasing the predictions, or can you release alpha hat? Is my question. Alpha
You
hat.
cannot release alpha hat.
Or some alpha which.
But releasing alpha will not be meaningful because each alpha is associated with phi xi, and I cannot release phi of xi.
Well, maybe we can take this offline. I don't think it.
Okay. So the second model is the semi-interactive model where the user the user sends a small sample from its test from its test data. And here what Kunal was saying was correct, that is we will indeed learn a kernel over these test samples. The test samples that we release that are given to us, and we don't have to worry about differential privacy of these test functions. We'll learn a kernel function over them. So the idea again is very simple, that we need to worry only about the output of each query, and we'll make each of these outputs differentially private, and the noise that we need to add will be very small because of low sensitivity of W hat. Okay, and now what we'll do is we'll try to find out a W, and in some sense a kernel over the test sets or test data points that I'm seeing that closely mimics the output that I'm looking for. So the guarantee is that epsilon delta differential privacy is clear, and also because of this small amount of noise that we need to add, what we can say is that, and because we have random samples from the test data set, that's why by taking a small number of those samples, what we can guarantee is that the performance of W private on my test data will be very similar to the performance of W hat, and it will be it is like the excess risk is given by something like 1 by root n epsilon lambda. Now here one thing which is at first seems very surprising, which is why do we have a lambda here, whereas in earlier bounds we never had a lambda. Like if you put lambda to be infinity, then the excess risk goes to 0. The explanation for that is that in the earlier case, the test set and the training set were coming from same distribution, and what we wanted was that our performance on this distribution is good. But here what we are saying is that our performance on the test distribution is as good as the performance of W hat. We are not claiming that we will give best performance on the test set. That is not possible because we don't even have any labels from the test set. All we are saying is that whatever the learner could have done in non-private setting, we'll achieve the same in differential privacy setting. And lambda tending to infinity makes sense, because if lambda is infinity, then my W hat didn't learn anything. W hat was 0, so W private can also be 0, and that's why I won't have any excess risk. But the risk of R W hat will be very large. Is that point clear?
So essentially you have kind of two error terms, one which comes just from the generalization from your training set to the test set, that's kind of hidden in RW hat, and then the second term is sort of coming from privacy.
So RW hat need not worry about training set distribution at all, right? W hat is something that I have learned. All I want to say is that whatever W hat could have done on my test distribution, W private should also be able to do that. W hat can be complete garbage, I don't care.
Right, but so just looking at the form, you'd be tempted to make lambda infinite, but you're saying R of W hat hides some dependency on lambda.
Yeah,
right?
So if I make lambda to be infinite, that says that W hat is not learning anything from the training data. So naturally my excess risk will be 0. But then the performance of W hat on the test set might be terrible. So in particular, let's say if I assume that my training set and test set have exactly the same distribution, then we can again apply the same sort of things, because we know that RW hat is bounded by RW star, the best I can do, plus some term that is dependent on lambda, like lambda r w plus excess risk, and then I'll trade off lambdas and get the error bound. But here all we are saying is that on test distribution we are doing as well as the non-private learner. Okay. And then finally we consider this non-interactive model, and here again we think of the problem is again that we want to figure out or we want to release a differentially private parameter vector W private, which essentially means that I want to I want to come up with a set of parameters so that for any query I can make this linear prediction in differentially private manner. So one approach that was suggested in this paper by Gupta, Roth and Ullman was that suppose if I could if I could generate queries which are worst case, that is which will make me enforce which will enforce certain updates, and because the number of updates that I can do is very small, so after a small number of such updates I will obtain a database or a parameter vector W private which is good, and which is good as in which performs well on unseen queries and which will be differentially private. However, for generating these worst case queries we need to use the exponential mechanism, and that leads to trouble because now we need to sample from a distribution of this type, and here all we know is that the inner product of phi z and wt is characterized by the kernel function for which we have certain parametric form, but we do not know how to efficiently sample from this distribution. So this distribution is not neither log concave, neither log convex. It's a very arbitrary distribution even for very simple kernels like Gaussian kernel or polynomial kernel. And so far we don't have any efficient algorithm for this setting. If the kernel function is a linear function, that is phi is an identity map, then you can certainly sample from this distribution using Gaussian, like using a mirrored Gaussian type of sampling. But then it's not very interesting because linear kernel anyways we can handle very easily. Okay, so but assuming that somehow we can sample from the distribution, what we observe is epsilon delta differentially private solution, and the utility is given by the excess risk that we have is given by this. And again the same caveat applies here, that what we want to do is we want to find a private vector W or privacy preserving vector W which is as good as possible or which is as good as W hat on the test distribution. And if we assume that the test distribution and training distribution are same, then again we can play this game of changing lambdas and obtain result. Okay. So let me just summarize what we have seen in this kernel function based DRM thing. So in general, like if I'm assuming that so in general I might need to use kernel function, and especially in machine learning kernel functions are very popular because they help in giving more accuracy. But if I'm not but if I don't have any control on how the kernel function comes, and let's say if I don't want to make any extra assumption, then the problem seems hard to handle in general. But we can relax it in three meaningful models. One is interactive model, another is semi-interactive model, and then there is non-interactive model. In the non-interactive model we have an inefficient method, and it would be interesting to see if we can come up with the efficient method to solve from to sample from the distribution that I described earlier. Okay, so let me now just summarize the entire talk. So empirical risk minimization is a very nice framework to study generalization error of several algorithms, and because it gives a very crisp notion of how good an algorithm is, that's why it's easy to understand or study differentially private algorithms also in this same framework. And goal of these differential private algorithms is preserve privacy and give small excess risk. And so for this problem we have seen several algorithms, and the interesting part seems to be that utility of all these differential private algorithms depend on the hardness of the problem, which is very critical. That if your problem is hard, then certainly differential privacy makes you lose quite a bit. But if your problem is easy, then differential privacy is almost comes for free. Okay. Now, in several of the bounds, we have a dimension dependent term which might not be avoidable in general, but assuming generalized linear model, tighter bounds are possible. And then there are several possibilities for applying differential privacy techniques in like kernel ERM, online learning, etc. So all these frameworks are very similar to this empirical risk minimization framework. Okay. So let me describe a couple of open problems that I think are very interesting. One time, okay. So one open problem is that even for the generalized linear model and objective perturbation algorithm, we needed to assume that the regularization function comes from a L2 norm ball, is L2 norm square, and the problem is unconstrained. So the question is, if I have any arbitrary strongly convex function RW and possibly constrained optimization problem, then can we achieve the correct regret or correct excess risk bound? Here again, there is a caveat: we don't know optimal dependence on epsilon. Okay. Another interesting open problem is that in practice, people do not do this regularized empirical risk minimization, especially if you are working on some really practical systems. A very naive thing to do is just take your empirical risk minimization problem, and without any regularization, you start from some random point and you start doing gradient descent. And rather than optimizing your function completely, you will just stop after some small number of steps. Let's say after 50 steps, you stop. Or what you do is you maintain a validation set, see how much error do you incur. So initially your error on the validation set decreases, and then at one point of time it starts increases. So at that point of time, you stop. And in fact, such early stopping methods have been analyzed in certain settings. For example, there is this work by Garvesh Rajkoti and Martin Wainwright. And then earlier there was a work by Lorenzo Rossesco and co-authors, which analyzed such early stopping algorithms. So one question is that can we use such early stopping algorithms for providing differentially private algorithms with good excess risk? And one simple idea can be that, let's say I have multiple random initialization of my empirical risk minimization approach. We run for some fixed number of steps, stop, take an average, and most likely the output that we give will be differentially private. The question will be how good it is, what will be the utility analysis of such an algorithm. That's not clear a priori. And another open problem that I feel is pretty important is semi-supervised or differentially private semi-supervised learning. So in supervised learning, we had this very simple or very generic framework of empirical risk minimization. So the canonical algorithm was very clear, but in semi-supervised learning, the canonical algorithm is not clear. However, there are some nice theoretically sound algorithms for this problem, such as this work by Nina and Avrim, and then there is also a work by Zubin, Gharamani, and Zerizu. So the question is, can we take those type of algorithms and come up with a differentially private algorithm with good excess risk bound or good generalization error bound, and at the same time which provides good privacy guarantees? Okay. So thanks a lot for your patience, and some of the papers can be downloaded.
More questions?
This early stopping idea that you mentioned, you seem to suggest that the privacy part, you suggested that you might know how to show that, but the utility is the problem. I don't see how you would possibly argue differential privacy for such an approach, because it always so that for a random point you just converge very quickly.
No, but that's why I said that you'll have multiple initializations. So let's say I'm running only for 50 iterations, and maybe I will have 1,000 random initializations. So then when I average it out, privacy should work out. So the simplest case is then when I'm taking just one step, and I'm not taking any step, and I'm just giving random initialization. So that is private. And then if I take one step randomly, then assuming certain properties about the loss function, again, I haven't proved it, but it seems like it should be possible to do. But the utility analysis definitely seems to be more challenging. Yeah.
I'll ask a similar question I asked Adam. What about something like data-dependent regularization?
Uh,
Do you think that would be, I mean, then you'd obviously have to make the regularization private as well, but.
Yeah, one example
So-
with data-dependent regularization in an unpublished node data
Oh, okay.
for the integration.
Does it work?
You can prove bounds.
You can prove.
But in some sense, early stopping is indeed a data-dependent regularization because you have a validation set over which you keep on checking score. Yeah. Yeah, Shasha?
So you were saying that for objective perturbation takes advantage of the convexity of the data.
Yeah.
Is there some sense in which you think that might be like it might be doing that optimally maybe? Or like, do you think that can be maybe shown? I mean, because you're saying the bounds are almost the same, right? I mean, like the worst case bounds are the same. There should be some way to bring out.
But
like,
the
how well is it doing
good,
with
but
respect to this data,
it's
right?
just that the bounds can be much better. Let's say I have a linear regression problem, and I know that the covariance matrix has, a condition number of the covariance matrix is very good. Let's say it's constant. Then that immediately adds to my strong convexity, and I will have much better bounds. Because the when I compute the strong when the bounds come up, you'll have something like a 1 by lambda n term. So this lambda is now much stronger. Like it's not just 1 by root n, but 1 by root n plus a constant. So
what I have in mind is Moritz and Aaron had these results for BCA where they have an algorithm that kind of optimally takes advantage of incoherence. So you could hope for something like that, right?
So you can get some analysis of, say, objective perturbation, assuming that the loss function is roughly quadratic and strongly convex around the optimizer, around the true minimizer.
Right.
There's no reason to think our analysis is, I mean, there's no reason that, there's no argument that I know of that shows that that dependency is optimal. Never mind the fact that it's not particularly clean either.
So it's not at that stage.
So let's take more questions to the coffee break and
Right.
we continue at 5:30.